Hi, good morning. It is me again with another chapter, which is illumination. Now, it's very important to know and understand all the formulas and definitions in connection with illumination. Now, if we look at the solid angle, which is omega, is equal to A divided by R squared, where A is the area and R is the radius. That becomes 2 pi 1 minus cos alpha over 2. Now, if we look at the radius and the angle, then we can determine the arc length. And that theta is our angle, is the length divided by the radius, which is the arc length divided by the radius, and that is given in radians. Now look at that little drawing there. If we've got an angle alpha with a radius and an arc length of L, then we can determine that. Then the next definition is candela. That is the unit of illumination intensity of a source. One candela emits 1 lumen per steradian. Therefore, the total flux emitted by the source all round is 4 pi lumen. Now, the luminous flux, F or phi, with the unit of lumen, defined as the flux contained per unit solid angle of a source of 1 candela. And then 1 lumen is more or less 0.0016 watt. Lumen hour, quantity of light delivered in 1 hour by a flux of 1 lumen. Luminous intensity, or I, or candle power of a point source in any particular direction is given by the luminous flux radiated out per unit solid angle in that direction. If d phi is the luminous flux radiated out by a source within a solid angle of d omega in any particular direction, then I is d omega dW, which is lumens per steradian or candela. The average candle power of a source is the average value of its candle power in all directions. The mean spherical candle power is the total flux in lumen divided by 4p, which is F divided by 4 pi. For a hemispherical, flux emitted in a hemisphere divided by 2 pi. The reduction factor F is mean spherical candle power divided by the mean hemispherical candle power. Now the illuminance or illumination is E. When the luminous flux falls on a surface, it is said to be illuminated. Illumination of a surface is measured by the normal luminous flux per unit area received. Now that normal means it's perpendicular. E is d phi divided by dA, or the flux divided by the area, which gives us in lumen per square meter, or lux. Now the luminance L of an extended source, L is delta E divided by delta IA cos phi, which is delta I over delta IA dash. And therefore E is I cos theta divided by square root D. Therefore the change of delta E is delta I over D squared cos theta. Now if we look at that little drawing there, if we have an illumination in a certain direction, falls on an area, now the cosine of that area gives the perpendicular area to the source. Now, if we substitute this value of delta I in equation 1, we get delta E is L delta A dash over D squared cos theta, which is L cos theta d omega. And that is delta A dash over D squared, is the radians. And therefore E is the integral of L cos theta d omega. And we can say it's L, the integral of cos theta d omega if L is constant. Now the luminous excitance M of a surface is defined at a point M on a surface is the luminous flux emitted per unit area in all directions. If an element illuminated delta A emits a total flux of delta phi in all directions over a solid angle of 2 pi radians, then M is delta phi over delta A. And M is equal to pi times L in the case of a uniform diffuse source. Transmittance T of an illuminated diffuse reflecting surface is defined as the ratio of the total luminous flux transmitted by it to the total flux incident on it. M is equal to T times E. Light falling on a surface is either transmitted, reflected, or absorbed. And the following relation holds good. T plus rho plus alpha is equal to 1, where alpha is the absorptance of the surface. The reflection ratio or coefficient of reflectance rho is given by the luminous flux reflected from a small area of the source to the total flux incident on it. So rho is equal to M over E, and that's always less than 1. It's 0 for a black body and 1 for a perfect reflector. Specific output, or the efficiency of a lamp, is the ratio of the luminous flux to the power intake. So lumens per watt is 4 pi F divided by omega, or watts per mean spherical candle power. Specific consumption, defined as the ratio of the power input to the average power, which is watt per MSCP. Now the luminance L of a diffuse reflecting surface, L is rho E over pi candela per square meter, which is rho E lumens per meter squared. Now laws of illumination. For a point source or a sufficiently away to consider it as such, E is then directly proportional to L, the inverse square law. E is directly proportional 1 over R squared. And Lambert's cosine law, E is directly proportional to the cosine of the angle made by the normal to the illuminated surface with the direction of the incident flux. Now, E is equal to I cos theta over R squared. Now, if we look at that little drawing of ours, we've got a lamp at a certain height, and then light falls on places directly underneath it and a little bit further away. So therefore, EA is I over H squared, because theta is 0, and therefore cos phi of 0 is 1. And then at point B, it is I times the length of B cos theta, and cos theta is H over LB. And that is I over LB squared times H over LB. That gives us I over h squared times h cubed over lb cubed, and that gives us I over h squared times h over lb cubed. And therefore 1 over h squared is EA, and h over lb cubed is cos theta to the third power, and therefore EB can be said to be E cos cubed theta 1. Similarly, EC is E A cos cubed theta 2, and so on. Just look at that figure again, where theta 1, theta 2, and theta 3 are the angles of incidence on B, C, and D. Now let's look at an example. A lamp giving out 1,200 lumen in all directions is suspended 8 meters above the working plane. Calculate the illumination at a point on the working plane 6 meters away from the foot of the lamp. So, because it says in all directions, we have to divide it by 4 pi. That gives us 1,200 lumens divided by 4 pi, which is 95.5 candela. Now, LB, if we use Pythagoras' theorem, is square root of h squared plus 6 squared, which gives us 10 meters. And then cos theta is 8 over 10, which is 0.8. And therefore, E is I cos theta over R squared. It's 95.5 times 0.8 divided by h squared, which gives us 1.193 lumens per meter. That is at 0.8. Example 2. A small light source with the intensity uniform in all directions is mounted at a height of 10 meters above the horizontal surface. 2 points A and B both lie on the surface. A is directly beneath the source. How far is B from A if the illumination at B is 1/10 as great as that at A? So there we have our drawing, 10 meters, and we want to know what is the illumination of B. So IA is, because it's directly underneath it, it's I over 10 squared, which is I over 100 lux. Now the length of B is the square root of 10 squared plus x squared, and therefore IB is 1/10 times 10 over the square root 10 squared plus x squared cubed. That gives us 10 over I, 10 divided by 10 squared plus x squared to the power 1.5. Now EB is equal to EA over 10. So therefore we have I over 1,000 is equal to 10I over 10 squared plus x squared to the 1.5. And if we solve for that, we find that x is 19.083 meters. Another example, a corridor is lighted by 4 lamps spaced 10 meters apart and suspended at a height of 5 meters above the center line of the floor. If each lamp gives 200 candle power in all directions below the horizontal, compute the illumination at the point on the floor midway between the second and the third lamp. Now, there we can see that it's a height of 5 meters, and then they are 10 meters apart, and therefore we can calculate what is the intensity at C. Now, since point C is symmetrically situated between the lamps, illumination at this point is twice that due to lamps 1 and 2. So I1 is I cos theta 1 over LC1 squared, and that is 5 plus 15. If we refer back to our drawing here, that's 10 there and 5 there. And L1 is that one. And that gives us LC1 is square root of 5 squared plus 15 squared, which is 15.8. And if we get the cosine of that angle, it is 0.316. Therefore, I is 200 times 0.316 divided by 15.8 squared. That gives us 0.254 lumens per square meter. And then at angle 2, it is I cos theta 2 over LC2 squared. So LC2 squared is the square root of 5 plus 5 squared, which is 7.071. And therefore, cos of theta 2 is 5 divided by 7.071, which is 0.7071. And therefore, I2 is 200 times 0.7071 divided by 7.071 squared, which gives us 2.828. And lamps 2 plus lamps 1's illumination gives us 3.082 lumens per meter squared. And therefore, IC is twice that, which is 6.164 lumens per square meter. Then if we look at two lamps, A and B, each of 200 candelas and 400 candela, respectively, are situated 100 meters apart. The height of A above the ground level is 10 meters and that of B is 20 meters. Compute the illumination midway between the lamps. So L1C is the square root of 10 squared plus 50 squared, which is 51. And the cos of the angle calculates to be 0.1961. L2 is 20 squared plus 50 squared square root, gives us 53.9 meters, and cos theta 2 is 0.3711. And therefore I1 is 200 times 0.196 divided by 551 squared, 0.0151 lumens per square meter. I2 is 400 times 0.371 divided by 53.9 squared, which is 0.0511 lumens per square meter. And the illumination at C is the sum of the two, which gives us 0.06215 lumens per square meter. Example 5, the average luminous output of an 80-watt fluorescent lamp, 1.5 meter in length and 3.5 centimeters in diameter, is 3,300 lumens. Compute its average brightness. If the auxiliary gear consumes a load equivalent to 25% of the lamp, compute the running cost of a twin unit for 2,500 hours at 3 cents per kilowatt hour. Now the surface area of the lamp is pi d squared over 4, which is the area, times the length. That gives us 0.04129 meters squared, 5, sorry. And the flux is 3,300 divided by the area, which is 80 times 10 to the power of 3 lumens per square meter. B is equal to flux divided by pi. That gives us 2546.8 candelas per square meter. And the total load for twin lamps is 2 times 80 plus, remember, the 25% of 80, which gives us 200 watt. The energy is P times T, which is 200 times 2,500 divided by 1,000 to turn it to kilowatt hours. Then we get 500 kilowatt hours, and the cost is the per unit cost divided times, the energy times the cost per kilowatt hour. And that's 500 kilowatt hour times 3 cents. That gives us 15 Rand. A small area, 7.5 meter in diameter, is to be illuminated by a lamp suspended at a height of 4.5 meters over the center of the area. Lamp having an efficiency of 20 lumens per watt is fitted with a reflector which directs the light output only over the surface to be illuminated, giving a uniform candle power over this angle. Utilization coefficient is 0.04, and therefore we must compute the wattage of the lamp. Assume 800 lux of illumination level from the lamp. So area is pi d squared over 4, which gives us 44.18 meters, where E is 800. So the flux is A times E, which is 44.18 times 800, which gives us 35,342.9 lumens. And F, flux, divided by the utilization factor, gives us 88360 lumens. And P, the power consumed, is 88,360 divided by the number of watts, number of 20, which is lumens per watt. So therefore that gives us 4,420 watts. Another example, a 100 candela lamp is placed 1 meter below a plane mirror that reflects 90% of the light falling on it. The lamp is hung 4 meters above the ground, and compute the illumination on the ground 3 meters away from the vertical under the lamp. So there's our little drawing. The mirror is 1 meters above, and remember the reflection from the mirror is 1 meters above. So the lamp produces an image L dash as far behind the mirror as it is in front. So L dash acts as a secondary source. Its candela is 0.9% of 90% of the 100 gives us 90 candelas. Now the illumination at point B is the sum of the illumination due to L and L dash. So the length of B in the first case is square root of 4 plus 3 squared, which is 5, and L dash B is 6 squared plus 3 squared square root, which gives us 6.708. Now EB is 100 divided by LB squared cos theta 1 plus 90 over L dash B squared cos theta 2. And therefore it's 100 over 25 times 0.8 plus 90 divided by 45, which gives us 0.9894, which gives us a total of 4.996 lux. A light source having an intensity of 500 candela in all directions is fitted with a reflector so that it directs 80% of the light along the beam, having a divergence of 15 degrees. Compute the total light flux emitted along the beam. Compute the average illumination produced on a surface normal to the beam direction at a distance from 10 meters. So the flux is 0.8 times 4 pi times 500, because it says there 500 watts in all directions. So that gives us 5027 lumens. Now the radius of the circle to be illuminated, R is P tan theta over 2, which is 10. Sorry, it's not P, it's L, I'm writing ugly. 10 tan 7.5, which gives us 1.1317 meters. And therefore the area is pi r squared, which is 5.445 meters. And therefore E is 5027 divided by 5.445, which is 923 lux. Right, example 9. A light is placed 3 meters above the ground and its candle power is 100 cos theta in downward direction, making an angle Q for the vertical. If P and Q are 2 points on the ground, P being vertically under the light and distance BQ being 3 meters. Compute. The illuminance or the illumination on the ground at P and Q and the total radiation sent down by the lamp. So first of all, we have LQ is the square root of 3 squared plus 3 squared, which gives us 4.24. The candle power along LP is 100 cos theta, which is 100 candela directly beneath it. And then E at point P is 100 divided by 3 squared, it's 11.11 lumens per square meter. Now along LQ is 100 cos of 45 because it's 3 and 3 meters, so that means it is 45 degrees, and that gives us 70.7. PQ is then 70.7 divided by 4.24, which gives us 3.933 lumens per square meter. Now the B part of the question is we've got a small hemisphere and ELQ is 100 cos theta divided by r squared. Now the area of the elementary strip at angular distance theta from the vertical and width of PQ is r d theta, which is 2 pi r sine theta times r d theta. That gives us 2 pi r squared sin theta d theta. So E is 100 cos theta divided by r squared times sine 2 pi r squared sine theta d theta, and that gives us 100 pi sine 2 theta d theta. And if we integrate from 0 to pi over 2, we get it at 314.12 lumens. And then example 10, a lamp with a reflector is mounted 12 meters above the center of a circular area of 24 meters in diameter. If the combination of the lamp and the reflector gives a uniform luminous intensity of 1000 lumens over the circular area, compute the maximum and the minimum illumination produced on the area. Right, there we have our little drawing, which is diameter of 24, height 12 meters. That gives us LB 13.71. EA directly beneath the lamp is 1000 divided by 12 squared, which gives us 6.944 lux. And at point B, it's I cos cubed theta over r squared. And because it's 12 and 12, it's 45 degrees again. So that gives us 1000 cos cubed of 45 divided by 12 squared. That gives us 2.455 lux. And then example 11. A lamp having a uniform luminous intensity of 200 lumen in all directions is provided with a reflector which directs 60% of the total light uniformly onto a circular area of 10 meters diameter. The lamp is 6 meters above the area. We must compute the illumination, 1 at the center and 2 at the edge of the surface with and without the reflector. Also compute the average illumination over the area without the reflector. So EA is 100 cos theta over r squared. That gives us 5.556 lumen. Then we can calculate cos theta, which is 0.768, and therefore theta is 39.81, and alpha is 2 theta. That means it's 79.61. So EB is I cos cubed theta over LB squared, which gives us 200 cos cubed 39.81 divided by 7.81 squared, gives us 1.486 lux. Now the reflector illumination at point A and B will be the same. Theta is 4 pi I, which is 2513.27, and I is 0.6 phi, which gives us 1507.96 lumen. Area is pi r squared, which gives us 78.54 squared, and therefore the average illumination is 1507.96 divided by 78.54, which gives us 19.2 lux. The average illumination without the reflector will be found first by determining solid angle subtended by the surface at the lamp, and then finding the luminous flux emitted in that solid angle. So omega is 2 pi 1 minus alpha over 2, 2 pi 1 minus cos theta, and that gives us 1.458. Remember, that's what we calculated there. Theta is 39.81. And IT omega is 200 times 1.458 gives us 291.58 lumens. And the average is total illumination divided by the area. That gives us 3.1712 lumens. And this concludes our examples on this illumination. Then I'll see you next time for the next exciting episode. Goodbye.